everyone. In this video, we're going to do a little bit of review of general acids and bases and then focus in on the structural characteristics and behavior of organic acids and bases. Okay. So you'll remember from chemistry last year that we defined an acid as a proton donor and a base as a proton acceptor. So for example, in this case, if I take HCl and I add it to water, right? This proton here on the HCl, it ends up on the water. So we end up with HOH. The unshared pair of electrons interacts with that on water, interacts with that proton on the HCl, forming H3O plus Cl minus. Right, so in this case, the HCl is acting as the acid because it is the proton donor, and water is acting as the base because it is the proton acceptor. Right, once the base has accepted its proton, it forms what's called the conjugate acid, which I'm going to abbreviate as Ca for short. And once the acid has donated its proton, it forms the conjugate base, or the Cb. Right, and then if something is acting as a base, it's accepting a proton. So in this case, for example, with the ammonia, the unshared pair of electrons on the nitrogen interacts with one of the hydrogens on water, transferring this unshared pair of electrons over there, or transferring this bond back to the OH. So I form OH minus and NH4 plus. So NHH, and this is NH4 with a +1 charge. So I've transferred an electron from water to ammonia, meaning that the ammonia is acting as the base, the water is acting as the acid, the OH minus is the conjugate base, and the NH4 plus is the conjugate acid, right? So anytime we see a reaction that's a proton transfer reaction, we classify that as acid-base, because our key thing here is we're transferring a proton. So if a proton is transferring, it's an acid-base reaction, which I'm just going to write like that. ABRXN, okay? So in this case, notice a couple of things about these two reactions that we just drew. Water is able to act as both a base and an acid, which means that it is amphoteric. So a substance is amphoteric if it can act as both an acid or a base, depending on conditions. So it can both donate and accept a proton. So water in this case is an example of an amphoteric substance, right? We've talked about this before, but just make sure we're okay. The acid minus a proton is the conjugate base. The base plus a proton is the conjugate acid. If an acid is something that donates a proton, we talk about the strength of an acid as being how easily or how readily that substance donates protons. So for example, if I have HCl, right? HCl is an example of a strong acid. So with HCl, right, all of this species of, so if an acid is a proton donor, we talk about the strength of the acid as being related to how easily or how much it donates protons, so how well it donates its protons. So if I look at HCl, for example, HCl is a strong acid, which means that in solution, most of this stuff has lost its protons. So it exists as H plus and Cl minus. It fully deprotonates, so it's all deprotonated. Because it's lost all of its electrons. It's called, not electrons, protons. It's because it's a strong acid. Right? Whereas something like acetic acid, which is here for acetic acid, that's a relatively weak acid, which means that actually most of it exists as acetic acid, and very little of it is actually in its deprotonated form of H plus and CH3COO minus. So it's actually mostly protonated and very little deprotonated. Now, notice a couple of things about the arrows that I'm drawing here. I'm actually drawing what are called equilibrium arrows. So equilibrium arrow, I'm drawing it like this. If it's 50-50, I'm going to draw the arrows like that. In this case, I drew the top arrow really tiny to indicate that very little of this species is actually deprotonated, and most of it exists as the reactant, as the protonated acid. Okay. So the strength of an acid, or in general, if we're talking about the strength of an acid, if the strength of an acid relates to how much it's deprotonated, if I have an acid HA that is deprotonating to form H plus A minus, the acid strength is going to be determined by the amount that is deprotonated. So the concentration of H plus times the concentration of A minus over the concentration of HA. This equals something called a Ka, and Ka stands for acid dissociation constant. The acid dissociation constant is species specific, right? This is something that is unique to each acid, and it doesn't change unless you change the temperature. So the higher the Ka, the larger this value for Ka, the more of this stuff is actually deprotonated, right? Because the higher the concentration of H plus and A minus, which means that the acid is stronger. So if you're looking at Ka values, higher Ka means you have a stronger acid. To compare, if I look at the Ka value for HCl, HCl has a Ka of about 10 to the 7th, whereas acetic acid, which I'm abbreviating as HAC for ease, has a Ka of 1.74 times 10 to the negative 4th, right? So for HCl, that means that the concentration of the deprotonated products, so concentration of ions, is 100 million times higher than the concentration of the HCl, which means it's in effect all deprotonated. Whereas with acetic acid, most of that is HA, and there's actually very little, a very small concentration of H plus and A minus is given by this number as being very, very small. Okay, so we can compare Kas, and that's okay, and it works, remembering that Ka is species specific, but these numbers get kind of annoying to look at. So for our purposes, and to make it easier on ourselves, we're going to look at something called the pKa and pKa values. So pKa, P in front of anything, remember, means negative the log, so is equal to negative the log of the Ka value. Right, so the pKa of HCl is equal to negative 7, and the pKa of acetic acid is equal to 4.76. Remember that these are from the numbers that we had on the previous slide. I just took the negative log of both and got minus 7 and then 4.76. So a couple of things to note. Remember that when we said that as the Ka increases, the strength of the acid increases. This case here, if I have a higher pKa because it's negative the log, that means that it is a weaker acid. Right, so higher pKa means a weaker acid. Lower pKa means a stronger acid. Basically, what the pKa is telling us is how readily this compound gives up its proton. Don't confuse this with pH. This is not the same thing as pH. pH, remember, is solution specific. It refers to the proton content of a particular solution. pKa is species specific, so every acid will have a different value for pKa. So in terms of acid strength and ranges for pKa values, typically if the pKa is greater than 1, less than 1, the pKa is less than 1, it's considered to be a strong acid. If the pKa is between 1 and 5, it's considered to be a moderately strong acid. The pKa is between 5 and 15, it's a weak acid. And if the pKa is greater than 15, it is a very weak acid, really not acting as an acid at all. Hard for it to be an acid and give up its proton. It's not going to readily do that. So let's take a look at the acids that we will see, looking at the organic acids that you'll see often. So for organic acids, there's really kind of two different functional groups that can act as organic acids. One of them is a carboxylic acid, which makes sense because it has acid in the name. Remember that a carboxylic acid looks like this, where you have some sort of alkyl group attached to a C double bond O with an OH group attached. It's this H right here. That is the protonate, that is the proton that is lost. It's the acidic proton. For carboxylic acids, sorry about that, the pKa's of carboxylic acids range from about 3 to 5. So they're moderately strong. They're relatively moderately strong, but not like HCl strong, but they do deprotonate to a significant extent. The other functional group that you'll see that can potentially act as an acid are alcohols. Now, alcohols, and as we know, have this group here and then an OH, and it's this proton here that could potentially act as an acid or a proton donor. This guy here, these guys are very weak. The pKa's of alcohols tend to be in the 16 range. So they really aren't acidic. You need a really, really, really strong base to strip a proton from an alcohol, but it can, in theory, happen. Just a side note, remember that both of these species here, alcohols and carboxylic acids, actually also have unshared pairs of electrons that they can use to accept protons. So these are actually amphoteric. So if these things were to accept a proton, right, if I were to have a protonated alcohol, for example, so if I have a protonated, what I have is this R, like, so for, let's say that I have a protonated methanol. So I have CH3, OH2, and this is a plus charge. So I've added a proton to the alcohol. The pKa of this guy is a negative 2.5. So this is a very strong acid. That proton, that extra proton will go away, and it will go away quickly. And if I have a protonated carboxylic acid, let's say that I have a protonated acetic acid here. So I put an hydrogen, an OH, an hydrogen on this, on the carbonyl oxygen. The pKa of this guy is negative 6.1. So if I protonate my alcohol or my carboxylic acid, these guys are very strong acids, which means that those protons are going to go away very, very quickly. It also means that they very rarely form because they're so strong. Remember that strong acids will dissociate. So these will dissociate, and so they very rarely form because they're so strong. Now, let's take a closer look at amines. The other functional group that we see that can act as an acid or base is an amine, right? So with an amine, here we have some sort of alkyl group with a nitrogen. Remember that this nitrogen up here has an unshared pair of electrons, and it also has a proton that it can lose, right? These hydrogens are attached to a nitrogen. They can technically be lost. These are technically amphoteric. However, the pKa of an amine that is not protonated, so like this is methylamine right here, the pKa of this guy is 40, right? So remember we said that things with a pKa of greater than 15 are not really very acidic. So this pKa is 40. This is not an acid. You're not going to get that proton to come out off very easily at all unless you're just not going to happen. Because it's just really, really hard to do. So this really isn't an acid. It could be, but it's not. It does not behave as an acid. But if I take this amine and I protonate it, so I take my protonated amine, the pKa of my protonated amine is actually equal to about 10. It's on the order of 10, which means that this protonated amine is actually a weak acid, which means that amines are basic. And in fact, they are the most common organic base that you're going to see is an amine, right? So amines tend to accept protons. They don't get rid of them. But to think about the strength of an acid or the strength of a base, we're going to think about this in terms of pKa, which means we're looking at the protonated amine as acting as the acid. Okay, so amines are organic bases. Carboxylic acids and alcohols can act as organic acids under different conditions. To give us an idea, remember that the pKa is less than 0 for protonated alcohols, for protonated carboxylic acids, and for H3O+. For the pKa is around 5 for carboxylic acids. It's about 10 for protonated amines. And it's about 15 for alcohols. Remember that amines, the pKa of an amine that's not protonated is 40. That's not an acid, so we don't really care. This is kind of the range in which we're thinking about things can act, that of pKa's where things can effectively act as acids. All right, so okay, when we look at these acids that have different pKa values, there's got to be something structurally that affects the strength of that acid, that affects the pKa of a particular acid. And there are three things three structural features that can affect the strength of an acid. The first is looking at the electronegativity of the atom that the proton itself is bonded to. So, for example, if I'm comparing a proton that's bonded to a carbon to a proton that's bonded to an oxygen, right? Remember that this guy here, this bond, because this oxygen is more electronegative, this bond here has an uneven distribution in charge. That hydrogen is already partially positive because of the uneven electron distribution, which makes this hydrogen easier to remove. Whereas with this guy, these electrons here in the carbon-hydrogen bond are actually relatively evenly electron distributed. So the electrons are equally distributed, which means that they're actually going to be very, very hard to remove. So the more electronegative this atom is, the atom that's bonded to the proton in consideration, the more acidic that proton will be. So hydrogens attached to carbon aren't really acidic. Nitrogen, but not really. More so than carbon, but not really. Oxygen, and then fluorine. Remember that the electronegativity of chlorine is in between the is a little bit less than the electronegativity of nitrogen. But we're looking at really this kind of thing. So if that hydrogen is bonded to an oxygen, it's more acidic than if it's bonded to a nitrogen. Okay, as we talked about before, because we have the pKa, we know the pKa of alcohols is about 15, whereas the pKa of the amine is about 40, right? So that hydrogen that's attached to the oxygen is way more acidic than the hydrogen that's attached to the nitrogen. Okay. The other thing that plays a role is the size of the atom that proton is directly bonded to. The bigger the atom, the more acidic the proton. All right, and this has to do with the electron distribution in the bonding orbital itself. So remember that iodine is larger, let's do it this way. Fluorine is smaller than chlorine, is smaller than bromine, is smaller than iodine, right? So this has to do with the size of the electron density within the bonding orbital itself. As the atom increases, remember that as the size of the atom increases, remember that we're bonding in valence orbitals, so they get larger, which means that the electron density within that bonding orbital gets smaller. So it's easier to remove the hydrogen from a larger atom because of the electron density is smaller. So that means that Hi has a pKa that's minus 10, whereas HF, the smaller atom, has a pKa of 3.2. Now notice a couple of things. Remember that fluorine is actually also way more electronegative than iodine. So in this case, it's the size of the atom that wins out over the electronegativity. If it's a bigger atom, it's going to be easier to remove, even if it's less electronegative than the smaller atom, right? The size of the atom wins here. Okay. So in both of these cases, we're talking about the atom that's directly bonded to the acidic proton, but it turns out that it also matters what's else is attached to that atom that's directly bonded to the proton. So let's take a look at, for example, acetic acid. So with acetic acid, right, we have, this is our acidic proton here, and this oxygen is directly bonded here. Now we know that this is way more acidic than an alcohol. So how can that be? Well, let's look at what else it's attached to. In this case, remember that there's a carbon attached over here on this side. Carbon's less electronegative than oxygen. This is a polar bond. Right? So this here, remember that the carbon-oxygen bond, which as we said is polar, makes this carbon have a partial positive charge. There's a dipole here that's pulling electrons towards this oxygen, right? So because of this dipole here from this COO group, this carbon is inductively pulling some of those electrons away from the oxygen. So it's in what we call inductively electron withdrawing. So through the sigma bond framework, right? So because this carbon is partially positive, it's actually pulling a little bit more of those electrons toward it from this oxygen, meaning that this hydrogen over here is easier to remove. So this electron density is actually pulled closer to the oxygen here than it would be if this if this group here was not present. So it's inductively pulling electrons away, making this hydrogen easier to remove, right? If I have an alcohol where I have, let's just say that I have a bunch of carbons and hydrogens attached to my alcohol, now all of a sudden that there's a partial positive here, but it's not because of the difference in electronegativity between carbon and oxygen, but it's not as inductively electron withdrawing because of the lack of anything else to remove electrons from this carbon. So it's not as inductively electron withdrawing, which means that this proton is going to be harder to remove than if it had something electron withdrawing over here. So if I take my alcohol and now I replace one of those hydrogens that I just drew with a fluorine, now all of a sudden it's more acidic, right? Because now this fluorine's partially negative, this carbon's partially positive, so it's more electron withdrawing with the fluorine than it is without the fluorine. And if I put the fluorine further away, or if I put the halogen further away, or if I put the electron withdrawing group further away, it's still going to help, but it's not going to help as much. So this alcohol here is a stronger acid than this alcohol here. It's still not a really great acid, but it's stronger than it would be without the presence of the fluorine. And then it would be with the fluorine that's further away. So if take a look at a couple of examples. So here we have two alcohols, one of which has a fluorine attached 2 carbons away and one of which has a bromine attached 2 carbons away. So the stronger acid here is going to be the one that's bonded to the more electron withdrawing stuff. This guy here, because fluorine is more electronegative, is more electron withdrawing than this guy. So this guy here is your stronger acid, right? Everything else being equal, the presence of the fluorine versus the presence of the bromine makes this more electron withdrawing and this more acidic. Still not a great acid, but it's more acidic than it would be otherwise. If we look here, the only difference between these two structures is that in this case we have 2 chlorines attached to this carbon, and in this case we have 1 versus 1. So in this case, these 2 chlorines are closer to here, right? They're both attached to this carbon, whereas one of the chlorines is further away over here, which means that this guy here is also going to be my stronger acid because those electron withdrawing groups are closer to the hydrogen. They're closer to the proton that is lost. So that makes it more inductively electron withdrawing, which means it's a stronger acid. Again, still not a great one, but stronger than otherwise. So, in addition to the structure of the acid playing a role in whether or not it's protonated in the pKa, so in determining how easy it is to remove a proton, it turns out that it also matters what atmosphere, what the solution is in. So the pH, the solution of the pH also plays the pH of the solution also plays a role in determining whether or not the acid is protonated or deprotonated in any specific set of conditions. So remember that pH is equal to negative the log of the concentration of H plus ions in solution, right? So this is talking about the conditions of the solution, that the acidity of the solution itself, right? And it turns out that the acidity of the solution, so pH, is equal to pKa plus the log of A minus over HA. Right, the log of this quantity, so the log of A minus over HA. This is called the Henderson-Hasselbalch equation. And we're not going to solve problems with this, but it helps us to get an idea of how much is going to be protonated and not, right? So if, for example, we're in a solution where the pH is equal to the pKa, in order for this to happen, this term has to be equal to 0. The log of 1 is equal to 0, which means that the concentration of A minus has to equal the concentration of HA. So it's 50% deprotonated. 50%. Right. If the pH is higher than the pKa, this is mostly deprotonated. Right, so the concentration of A minus has to be greater than the concentration of HA in order for the pH to be higher than the pKa. So it's mostly, if the acid is in a solution where the pH is higher than the pKa, it's mostly deprotonated. And if the pH is 2 units higher than the pKa, so let's say that if the pKa is 4 and the pH is 6, then it's pretty much all deprotonated. You have 100 times more deprotonated than you do not deprotonated, so that's considered the cutoff. If it's greater than 2 pH units, if the pH is greater than 2 units above the Ka, or the pKa, is considered to be completely deprotonated. And remember that if the pH is less than the pKa, again, so in this case, it's mostly unprotonated, right? So it's in its acid form. So you have mostly HA that exists if the pH is less than the pKa. If the pH is greater than the pKa, you have mostly A minus that exists in solution. Again, the 2 pH units, or 2 is the cutoff for what's mostly deprotonated or what's mostly not. If the pH is within 2 units of the pKa, it's a mix. You have both species present. If it's greater, or if it's more than 2 units away, then you have one or the other. All right, so does it matter? Why do we care whether or not a species is protonated or deprotonated at a particular pH, or whether it's acting as an acid, or it's what form it's in? Remember that whether or not something is charged turns out to have a huge role in its physical properties, thinking solubility, thinking all that stuff. So if I have a mixture and that has a carboxylic acid and an amine in it, and I have that mixture that's at pH at 2, right? That means that both of these species, if we look at this as a pKa of 4 and this is a pKa of 10, are in their acidic forms. Which means that the carboxylic acid the amine itself is charged. It's NH3+, whereas the carboxylic acid is not charged, right? So the amine will dissolve in water much more readily than the carboxylic acid, which is not charged, right? So for example, if I wanted to separate this mixture of my carboxylic acid and my amine, both of these things, I could dissolve them both in some organic solvent like ether. I could add an acid, so I could add a little bit of HCl. The HCl will not dissolve in the ether, but it will dissolve the amine. So the amine will end up in the water layer, whereas the carboxylic acid will end up in the ether layer. Right? Vice versa, if I'm at pH of 12, they're both deprotonated. Which means that the carboxylic acid in this case will be charged and it will end up in the aqueous layer, whereas the amine will not be charged and it will end up in the organic layer. We're going to do this in the lab coming up, where we're going to separate a mixture of 3 materials using what's called an acid-base extraction, which is this idea here of mixing an organic layer with an acid and with a base to separate out based on solubility. So in our next class, we'll go over this and any questions that you have about the contents of this video, and along with doing some practice working with pH and pKa and determining what's protonated and what's not protonated under different conditions.